In order to determine a particle's change in velocity, we have to do something called integration. And we do that by examining graphs in motion analysis. And we can look at graphs of acceleration versus time, or we can look at graphs of velocity versus time to determine either a particle's change in velocity or change in position respectively. So when we integrate something, that is another calculus topic. And we're going to learn sort of the basics of integration, and then we will look at some example physics problems. So integrating acceleration, we're going to talk about basic integrals and how integrals as acceleration versus time are applied into physics. So the area problem of an integral calculus. So if we have a function that is a curved function, we sometimes need to know the area underneath that curve. Now, that can be a bit challenging because it's a curved line. And the best way, or one way that we can approximate that area is by shading in the area, not exactly along the curved line, but uh, we can write these rectangles in there and figure out the total area by finding the individual area of the rectangles and then adding them all together. Here we can see that we want to find the area between this interval, between when x is 0 and when x is 3. So we want to find the area under the curve between here and here. So it actually includes all of this. And so we can estimate with these rectangles. So there's 1, 2, 3, 4, 5, 6, 7, 8 units all together. So that's kind of the beginning of what an integral is. Um, we write integral notation like this. So the upper limit is where we're stopping at. So for the interval 0, 3, like in the last one, our upper limit is going to be 3. Um, the lower limit of integration, or we can think of it kind of as our starting value of our interval, is going to be 0. And so that goes there. And then this function from here, the function is f of x equals x squared plus 1. So the function is this parabola here. And so we write that function here at x squared plus 1, and we're finding the integral of it, and we write dx there. That's the variable of integration is what that's called. This is called the integrand. It's basically just the function that we're finding the integral of. And this is the integral symbol. So the integral between 0, 3, we write it like that, and the derivative would be equal to 2x. So if we wanted to find the derivative, again, quick review, we bring the number down, multiply it by the coefficient in front of the term. The integral is essentially the opposite of the derivative. So we increase the power. Instead of subtracting by 1, we add by 1, and then we divide by what that total power is. So in this one, we would have x squared plus 1 and divide all of that by 3. And we do the same thing for this number 1. So now the number 1, technically, if we wrote it as a variable, it would be x to the 0. Anything to the 0 is just 1, so it would be 1 times 1. But if we have x to the 0 and we add 1 to it, now it's x to the 1. And if we divide by that power, it's just over 1. And so we don't need to write the over 1 there. We just write 1x to the 1, or 1x, or even more simply put, just x. So it simplifies to, we had x squared plus 1 over 3. This is x cubed over 3 plus x. Now we have to substitute in the values of the interval where x is between 0 and 3. And this is how we can find what that shaded region is. So we're finding this is called a definite integral. So we're finding the amount of the area under the curve. And we're finding that area between a certain interval. We're checking between 0 and 3. Earlier, we used that rectangles method, and we estimated that our answer was going to be about 8 for the area. So here's how we write this now. So we found the integral of this. Now we're saying this is the integral between 0 and 3. And all we do next is we plug in 3 for x, and we find out what that value is. And we plug in 0 for x, and we find out what that value is. And then we subtract the difference. And so after doing that, we get 27 over 3 plus 3 for when we plug in 3 for x, which is 9 plus 3. And then when we plug in 0 for x, we just get 0 cubed over 3. 0 plus 0 gets us 0. So this ends up being 9 plus 3 minus 0, which is 12. So our final answer, our approximation was only 8, and our final answer equals 12. So that's the exact number of units that's going to be under the curve of the function f of x equals x squared plus 1. Let's look at some other examples of integrals here. So that was one example. We'll do maybe one more together. So here it says evaluate the definite integral. And it looks like it gives us an interval from -1 to 3. That's what it looks like to me when we're looking at where it's shaded. So the interval is between x equals -1 and x equals 3, and this is the integral. So we're going to write this in the notation. First, we have to find the integral of this function. So we're going to increase the power by 1, divide by that total amount. Increase the power by 1, divide by that amount, whatever the power is, and then increase the power by 1, divide by that amount. And so this is our integral of the function -x cubed plus 3x squared plus 1. Now we want to find what the integral is between -1 and 3. So we're going to plug in 3 for x. We plug in 3 for x. We get 9.75. All we're doing is we're just plugging in that value for 3 and finding what the value is when x equals 3. So what the integral is when x equals 3. And then the same thing for when x equals -1. So we're going to plug in for what -1 is, and that's -2.25. Then we subtract the difference between the two. Here we have a double negative, and we just so happen to get the same answer of 12, but this is a completely different function, and that's 12 units underneath the interval -1 and 3. All right, here's another example. This is more closely related to what we're going to be doing in our physics class. Is we're going to see these graphs of time and velocity, and we have to find the integral. So if we have a velocity time graph and we find the integral of it, it's like going backwards from the derivative. So before we talked about the derivative being if we have displacement that is equal to, well, let me see here. We have displacement, velocity, and acceleration. The derivative of displacement equals velocity. But we can go the other way around with the integral. So it goes in the opposite direction. Here we have velocity and time. And if we find the integral of the velocity time graph, now we can understand what the displacement is. So we're going in the other direction. So we go this way for derivatives, and we go the other way for integrals. I think that's probably the easiest way to remember those. So as we take the derivative of displacement, we get velocity. As we take the derivative of velocity, we get acceleration. And then going the other way, if we take the integral of acceleration, we get velocity. If we take the integral of velocity, we get displacement. And that's what we're doing in this problem. So we are finding the integral of velocity, which is displacement. All right, so we want to find what's the area under this curve. And this is actually, it's not a curve, but we want to know what's the area under the function from 2 to 4 seconds. So 2 seconds is here, 4 seconds is here. And we can do one of two things. We can say, we can find the area of this as a trapezoid now. So you can find the entire thing at once, or actually, yes, we have to do both pieces. So we have to do the trapezoid plus the area of the rectangle. So the area of the trapezoid is 1/2 of base 1 plus base 2 times the height. So you can think of this thing as flipped on its side. This is one of the bases, and this is one of the bases of the trapezoid. If you turn it over, this becomes the height of the trapezoid. So we do 1/2 base 1 plus base 2 times the height to get the area of this trapezoid in black. And then area of rectangle, simple enough. That's just base times height. So we're going to add those two together to find the integral. So here we don't even have the function. It doesn't tell us what the velocity function is. It just shows us a graph. And so we can now calculate the integral without a function just by looking at the graph. We can separate it into manageable pieces and figure out the area. So for the first part, the area of the trapezoid is 1/2 base 1 plus base 2 times the height. So we have 1/2 times base 1 is 2. So this is just 2 units up. And notice these are going up by 1/2. So base 1 is 2. Base 2 is 4. So 1/2 times 2 plus 4 is just 1/2 times 6. And then the height is going from 2 to 3. So the height's just 1. So 1/2 times 6 times 1 gives us 3 for the area of our trapezoid. For the area of the rectangle is base times height. So now this is 1 times 4, which is just 4. So now we have the area of the trapezoid and the area of the rectangle. 3 plus 4 gives us a total area of 7. All right, and then these were just some other practice ones. I'm going to skip through these because we have gone over a couple of examples already. Skip through these. All right, so again, when we integrate acceleration, velocity is the integral of acceleration. I showed you guys the order of what we go in. We go from displacement to velocity to acceleration when we're talking about derivatives, and it's the opposite direction when we're talking about integrals. So velocity is the integral of acceleration. We're given a graph of if we're given a graph, we can find the acceleration by integrating the graph on at any given time. So we can write, this might be getting into a few more proofs now. I'm going to just kind of go a little bit forward here. This is referred to what's called a definite integral. So a definite integral tells us between what two times or between what two x values is the area going to be. So that's what a definite integral means. And this is just a short proof about how we go from we can we can go from acceleration and change to velocity. So uh, this is just showing you that meters per second times seconds equals 1 meter per second. All right, so if we integrate velocity, displacement is the integral of velocity, and we've talked about that a couple of times already. So this is our official formula for that. And again, we can find the definite integral between two different times. All right, now to our example problem. So there's kind of a lot going on in all of these example problems, but I think this is a great example problem. Um, Whiplash injury is injuries that people usually get from when a car um, when they get rear-ended from somebody when they're driving a car. In the 1970s, researchers found that the injury was due to the person's head being whipped back over the top of the seat as the car was going forward very fast. So we built these head restraints on cars now to prevent neck injuries when rear end collisions are happening. In a recent test to study neck injury in rear end collisions, a volunteer was strapped to a seat and then moved abruptly very quickly to stimulate or to simulate a collision by a rear car moving at 10.5 kilometers per hour. And here's the figure of what that is. So here's acceleration and here's time. And it gives the acceleration of the person's torso and head during the collision. So let's take a look at what's happening here. It says the torso acceleration was delayed by 40 milliseconds because during that time, the seat had to compress against the person. So their body didn't move even when the crash happened. So they they didn't make the person go very fast. They were just going 10.5 kilometers per hour. But then the the person's body, it moved once it was pushed, but there was a delay of 40 milliseconds because the seat kind of pushed into the person's body a little bit. And then the acceleration was delayed by an additional 70 milliseconds. So the the head acceleration was delayed by an additional 70. So that means from here to here is there the person's head didn't move at all. So you can think of it as they were they were strapped to the seat and then someone pushed them not very much, but still they got a decent push. And this is what happened. So their body didn't move at first for 40 milliseconds. That's a very short amount of time. And then their body did move, and then their head started to move a little bit later, 70 milliseconds later, or 110 milliseconds from the very start. So we want to figure out what's their torso speed, or that means the person's body, what that speed is when their head started to accelerate. So we have some given information. We know the initial time is 0. We know the initial velocity is 0. We know that our time 1 for the person's head moving is 110 milliseconds, but we don't know velocity 1. So we're trying to find what the torso speed was when the head began to accelerate. So the head began accelerating at 110. But we don't know what the velocity was. So we're trying to find the torso speed when the head began accelerating. So we're going to write this integral formula. The change in velocity is the area under the acceleration versus time graph. So we're going to write the formula for the integral is the velocity minus the initial velocity is the integral of acceleration. So this basically just means that our our velocity minus our initial velocity is the acceleration area between the initial time and the first time. Now there's our initial time is 0, and our first time T1 we wanted to know was when it was at 110 milliseconds. The area is 0 from 0 to 40 milliseconds. There's no area that's been covered there. There's only area here. But if there was area here, we would shade that in as well. So because our initial velocity is 0, we can simplify this to just velocity is the integral of acceleration from our initial time to our time 1. The head begins to accelerate at 110 milliseconds. And so now we're going to calculate the integral between the intervals 0 and 110. And that's not too bad of a calculation, especially considering that we've gone over a couple of examples of integrals, of definite integrals previously. So we're just going to find the area of part A plus part B plus part C. So here's part A. There's no area from the interval of 0 to 40. For part B, from 40 to 100 is this is now a this is a triangle. So we're going to do 1/2 of the base times the height. And so and you can do it either way. You can say this is the base or this is the base. Either way is fine. But right here here's T1 is at 110. So this is going to be at 100. And so this is 60 milliseconds have gone by from here to here. Now, you have to convert this to seconds because our acceleration is in terms of meters per second squared. So our milliseconds is 1/2. We're going to do 1/2 base times height. So the base is 0.06 seconds. So that's 60 milliseconds. That would be the same thing as 60 milliseconds. So 1/2 times that times 50 gives us 1.5 meters per second for our second portion for area B. For the final portion for area C, that's just a rectangle. So we have 0.01 seconds times the height of 50 meters per second squared, and that gives us 0.5 meters per second. So now we have 1.5 meters per second and 0.5 meters per second. So the total area between the starting point and 110 milliseconds, the total area is 2 meters per second. Is 2 meters per second. So what happens is these units cancel with seconds and seconds squared, and we're left with meters per second. And I believe I made a small error there. That should just be meters per second to the power of 1. All right, a final note on integrals. The integral, again, is the area under the curve. For rectangles, the formula for rectangles, base times height, triangles, 1/2 base times height, and trapezoids is 1/2 times base 1 plus base 2 times the height. And here is the workbook assignment associated with integrating motion analysis.